problem, I shall say. Now, often this type of problem, this denesting problem, is written in the squared form. In this case, 37 squared is one more than the radicand you see right there, 1368. 37 squared is actually equal to 1369. Now, actually, it's not that important to even know that, but the problem just kind of looks a little more enticing, you know. But 37 squared is 1369. And so sometimes you'll see it written as the square root of 37 squared, all right? So that looks nicer, I guess, or more attractive in some sense. Okay, and again, that would allow you to write this as the square root of 37 squared. The square root of 1369. The square root of 1369, and so you have the consecutive numbers there. I just choose to write like this. It's a little bit easier to process it. Now, y'all, denesting just means to remove this top radical, all right? Now, it makes a lot of sense that this algebraic identity would come into play right here, because when you take the square root of an object squared, you just get the object as long as it's a positive number. It's technically that definition of absolute value, but you really don't have to worry about that here, since this number is bigger than this one per this comment right here. Now let's keep going here. Now what turns out to be useful that I haven't seen on the other channels is to write down the prime factorization, of 1368, which is fairly easy to do on your own. It takes some time, and I didn't show the work, but you get 2 times 2 times 2 times 3 times 3 times 19. Now you could write this in the prime factorization format, but it's a little bit easier just to, you know what I mean? You could write this as 2 cubed if you wanted to. But I didn't see that it was lent any more insight to write it that way. You could write this as 2 cubed times 3 squared times 19. But again, that's not really any help as far as I can tell. It's easier just to leave it in the non-exponential form. Okay, now you can see what I did. 1368 is equal to this, but 2 squared, 2 of the 2's is 4, and you take the square root of that and you get 2. That's where this 2 comes in. Notice that you're just left with 2 times 3 times 3 times 19 here. Okay, now the a squared plus b squared is going to be an integer, so we equate the integer part to the integer part right here. You see a squared plus b squared is equal to 37. Now, I don't know if this always really works. You know, I think it only works if you have 4. The radicand is a multiple of 4. But in any event, it works, and it does work in this case. And also, we equate right here. You see, you have a minus 2 here and a minus 2 right here. So it's just dead on obvious that you would equate the product AB to the square root of 2 times 3 times 3 times 19. Okay? See how we're not even working with the number itself, we're just working with the prime factorization. Now, a couple of facts here that come in super handy. A squared plus b squared equals to 37 implies that both a squared and b squared would have to be less than 37. Okay? Probably could say less than or equal to 37. Okay, but what really comes into play right here, what really stands out here, is that 19 is going to have to stand alone. Otherwise, if you multiplied 19 times any of these other numbers to get a divisor, you would get a number bigger than 37. You know, 19 times 3 is what? 57. 19 times 2 is 38. So you see 19 has to stand alone, and so that forces the assignment of a is equal to the square root of 19. Notice how non-algebraic this is. The other channels kind of force-fitted this just by trying to do some algebra, and you could tell they just really already knew the answer. See right here, this is the only possible assignments that could work here, and you don't even have to do the calculations out. So you would have a is the square root of 19. Now notice that has to add up to 37 is another way to really keep track of this, and b has to equal to the square root of 18. Now notice that's equal to 2 times 3 times 3. Okay, so a is the square root of 19, b is the square root of 18. Like this. And again, folks, everything is satisfied without having to do any calculations. And I know you're saying, well, you know, you just knew the answer. Well, yeah, I made the problem up. But notice that there's no other divisor possibilities. 3 times 19 would be 57, and you would have 6 here, and 57 and 6 don't add up to 37, right? So this can be solved just by pure analysis of the prime factorization. Now, if it wasn't the case that 19 were so distant from the other prime factors, you'd probably have to worry about other combinations. But these are the two choices. And so what we're going to get right here is that this would be equal to the square root of 19 minus the square root of 18. Now, again, I think it's pretty cool that you can just think of it as a prime factorization problem. I really do. I know I'm repeating myself here, but a lot of people just try to dive into the algebra and wave their hands and say, okay, it has to be this pair of numbers, but it's not really clear. It could be other pairs of numbers, but if you do the prime factorization, you see there's no choice but to do 2 times 3 times 3 equals 18, and then 19, because 19 cannot stand with any of the other factor pairs, otherwise it would produce a number much bigger than 37. Well, you would get a possibility would be 2 times 19 is 38, and then 9 there, 38 and 9 is 47, right? So it has to equal, it has to sum, the squares have to sum to 37, and that eliminates the possibilities to these two choices. So anyway, this is final answer, folks, and we have denested it. Notice this represents a denesting. There's only a pair of radicals here and no overarching radical. So that's the solution.